Hey everyone, and welcome. So, have you ever stopped to think what the water coming out of your tap has in common with, say, the air that's holding up a massive 400-ton jumbo jet? Well, they're both fluids. And today, we're going to dive deep into the hidden and honestly super powerful science that governs absolutely everything that flows.
All right, to get us started, I've got a little puzzle for you. What's the one invisible force that connects the massive lift of an airplane wing and the wicked curve of a spinning cricket ball? I know, it sounds kind of impossible, right? But stick with me, because by the end of this, you are going to know the answer.
Okay, so first things first. Let's start at the very beginning with the most fundamental question: what is a fluid, really? The answer might actually surprise you with just how simple it is.
Well, to put it simply, a fluid is just anything that can flow. That's it. So that means both liquids, like water, and all the gases, like the air that's filling our atmosphere. Yep, they're all fluids. And the big secret they share, it's that they offer almost zero resistance when you try to change their shape.
And this really gets to the heart of it. Think about it. If you push on a solid wall, what happens? It pushes right back. It resists you. But if you push on water, it just flows. It gets out of your way. And that one simple property, that difference, is the key to literally everything we're about to talk about.
All right, so now that we've got a handle on what a fluid actually is, let's dig into one of its most powerful properties, especially when it's just sitting still. Let's talk about pressure.
And to really wrap our heads around this, let's think about something we've all experienced. Why is it that a sharp needle can pierce your skin with almost no effort, but if you take the back of a spoon and push with that exact same force, pretty much nothing happens?
The answer, my friends, is pressure. See, it's not just about how much force you're using. It's all about how concentrated that force is. You take a little bit of force and focus it on that teeny tiny area of a needle's tip, and you get this immense pressure. But that same force, spread out over the much larger area of a spoon, it does almost nothing.
Let's really break this down to see how powerful it is. You just take a relatively small force.
You concentrate all of that force on a really tiny area.
And bam, you create a pressure that is just immense. I mean, get this. The weight of just the upper body of a 40-kilo person creates a pressure of 200,000 pascals on their thigh bones. That is nearly double the atmospheric pressure we're all feeling right now, every single day.
Now, this whole idea of pressure leads to some applications that honestly feel like magic. I mean, how on earth can that tiny little push from your foot on the brake pedal possibly stop a 2-ton car?
Well, the secret here is something called Pascal's law, and it's the whole principle behind hydraulics. It works like this. You apply a small force to a small piston, right? That creates pressure in an enclosed fluid, like your brake fluid. Now, since that fluid can't really be compressed, that pressure gets transmitted equally everywhere inside the system. And when that same pressure pushes against a much bigger piston over at the wheels, it generates a massively multiplied force. The fluid literally becomes an incredible force multiplier. It's genius.
Okay, so we've seen what fluids can do when they're just sitting around. But things get really interesting when they start to move. So it's time to, you guessed it, go with the flow.
Now we're going to focus on a specific kind of motion called streamline flow. The best way to picture it is like perfect, orderly lanes on a highway, but for fluid particles. Each little particle follows its own smooth, predictable path, and this is the crucial part, those paths never, ever cross. It's a nice, tidy, orderly kind of flow.
Okay, so the first rule of this orderly flow is something called the equation of continuity. And all it really says is, what goes in must come out. So if you have a fluid that can't be compressed, like water, and the pipe it's in suddenly gets narrower, well, that water has no choice but to speed up to keep the same amount flowing through. It's the exact reason why putting your thumb over the end of a garden hose makes the water shoot out so much faster.
And you know what? That one simple idea that fluids can change their speed brings us right back to that mystery I mentioned at the very beginning. We are about to uncover the secret of flight.
So, here is the critical question. We now know that when a fluid is forced through a tight spot, its speed goes up. But in physics, as in life, there is no such thing as a free lunch. If the speed goes up, something else has to go down. What is it?
The answer is pressure. And this right here is the legendary Bernoulli's principle. In the simplest possible terms, it means that where the speed of a fluid is higher, its pressure is lower. They are completely linked, but in opposite ways. Honestly, it's one of the most powerful and kind of counterintuitive ideas in all of physics. And this is how an airplane flies. An airplane wing, an aerofoil, is shaped very specifically to take advantage of this principle. That curved top surface forces the air to travel a longer distance, which means it has to speed up. And what did we just learn from Bernoulli? Faster air means lower pressure on top of the wing. Meanwhile, the slower air moving across the flat bottom creates higher pressure. And that pressure difference, that creates a net upward force. We call it lift.
And this brings us right back to our spinning cricket ball. It's the exact same principle at work. As the ball spins, it actually drags a thin layer of air around with it. On one side, that spinning motion adds to the airflow, making the air go faster, creating low pressure. On the other side, it fights against the airflow, slowing it down, creating high pressure. The ball is literally pushed by the air from the high-pressure side to the low-pressure side, and that's what makes it curve in midair. That's the Magnus effect for you.
All right, for our final section, let's look at two more properties of fluids that are a little more subtle, but just as powerful. We're talking about their stickiness and their stretchy surfaces.
So viscosity is basically just a fluid's internal friction. It's how much it resists flowing. You've got low viscosity fluids like water that flows super easily, and then you have high viscosity fluids like honey that flow, well, really slowly. It's why trying to stir a jar of honey is so much harder than stirring a glass of water.
And finally, we've got surface tension. Now, this is a really fascinating property. It's where the molecules right at a liquid's surface have a bit of extra energy, and it makes them all pull together really tightly. This creates a kind of elastic skin on the surface. It's how some insects can literally walk on water. It's also why raindrops pull themselves into perfect little spheres as they fall. That's the most efficient shape with the least surface area. This force is even strong enough to help pull water and sap all the way up to the top of tall trees, completely defying gravity. Pretty amazing, right?
So there you have it, from the pressure that lets you stop a 2-ton car with your foot to the principle that lifts that same car if it had wings into the sky. The whole world of fluids is governed by just a few really elegant and powerful rules. And the cool thing is, they're not hidden at all. They're right there in front of us, working all the time. So the only question left is, now that you know the rules, what other parts of your world can you explain?